Hello, everybody. Welcome to Fingi number 4. I am Joosep Kivastik, and this is Henrik Erbais. And today we're talking about the paper that Henrik chose, which was a long paper. It says language models are a few-shot learners. Which, now that I think about it, it's a weird title for the paper a bit. But yeah. So the paper basically is from OpenAI. I hear myself, Henrik. It's a paper from OpenAI, and it's basically now talking about training GPT-3, and so which is now their largest one. It's 175 billion parameters. And few-shot learning is basically that they're showing it several examples. So there are different. So basically, they're trying to figure out if it after training it can generalize to some kind of tasks, new novel tasks. And there are like a few ways to do it. There's zero-shot learning, where basically they're giving it a new task and seeing if it can, without ever seeing the task before, it can solve that task. Then there's one-shot learning, where they show it one example. They call this conditioning. Maybe later Henrik can say what conditioning is. I was a bit. This paper didn't explain what it is exactly, so I'm a bit confused on that part. And with few-shot learning, they give it several examples to condition it on. So there is no training happening during conditioning. So there's no fine-tuning, but it kind of just prepares the neural network to accept this new exercise. So yeah. Do you have anything to say?
I was fixing my sound. I hope it's better now. But yeah, the main part of this different shots are basically kind of the speciality of transformers, which we haven't, I think, either of us looked into too much. We just know that
attention is all you need.
Yes, exactly. The best paper title ever. I think this is almost like this title is probably inspired by that title, where it's like you make like a strong statement in the title. It sounds very similar. So it's like the these different, let's say, ways of how they give data in probably affect the neural network so much because of the transformer architecture. Because it basically fills it with well, attention or context or whatever, which then activates the neural network differently.
Yes, this is the first figure is about this as well. So they call it the inner loop and the outer loop. So outer loop is the, I guess it's the training part, where they're using regular methods to train the neural network and loads and loads of data, which is what GPT-3 is all about. And then they have this inner loop, where they call it in-context learning. So where they're like priming the system depending on the task. So for example, they're showing that 5 + 8 = 13, and etc. And then they will have, so for example, an addition task with different numbers to see how it will actually cope. Can it actually do addition? And then it has different example intervals. So for example 2 or sequence 2 shows word scrambling. So if you have BRID coming in, then this should be outputted as a bird. And sequence 3 shows translation. So yeah. And
I think before we go into, let's say, examples and details even, maybe would be I think the kind of story that they put in the introduction was also quite nice and a cool intro to the paper, which is basically GPT-3 is almost equivalent to GPT-2 from a network architecture point of view. But the main hypothesis is that you don't necessarily need to fine-tune networks for specific problems, but you can just scale the whole network up bigger and bigger, and that it will work better, and B, the second hypothesis is that it will generalize to many different tasks. I would say both of those, like that hypothesis was a pretty cool hypothesis, actually. I don't think many people believe that, and they kind of showed, oh, by the way, this works.
Yeah, I think isn't that the main idea behind all of the GPT? Just throw more data at it to make it bigger.
Yes, but at the same time, transformers aren't that old. So it's like in this framework with this approach, keep scaling it. I would put it somewhat like that.
Yeah,
so it's not just one thing. It's like with this network, it scales well, it generalizes well, which is pretty interesting.
And even afterwards, there are a few figures where they show that it still scales to the power law that they presumed a while ago. So currently still on track to scale further if there is enough data, and yeah.
I think most interesting was also that they scaled mostly with the network size, not necessarily with the amount of data, right? I think they somewhere they showed also described that they actually used less data.
I think the data was better paired at least.
Yes, I think under one of the images they quickly mentioned it also that actually. Yeah, under this 2.2 where they talk about the total compute. We can talk about that later then. But yeah, the hypothesis was cool, and they were rewarded for this assumption of, let's say, other let's say, scaling was also shown, but they did like a 10x scaling, which is more costly, let's put it like that, doing a 10x scaling. And I would assume that when they launch GPT-4, they'll do another 10x scaling. If they go with the same approach. Some other interesting stuff was because they don't do fine tuning, then they don't need kind of very specifically labeled training data for specific tasks, but just a lot of data, a lot of unsupervised learning, which is I would claim scales better than fine tuning for problems. If we talk about collective resource usage, this thing scales better than having 10,000 researchers figuring out specific edge cases to solve. If you think about it like that.
But in the end, you still, if you actually want to, let's say, use this, you will still fine tune it most likely for for your thing.
Maybe, but you might fine tune it.
You will distill it. You will distill it first, and then you will fine tune it.
Yeah, that's what they recommend as one potential, let's say, future direction. We can probably cover that in the end. What future directions they have in mind, and we can make bets on what they will do for GPT-4 based on this data.
More parameters.
Yeah, just put 10 next and see what happens. That would be actually interesting, but probably not interesting enough.
Well, as long as it scales. So yeah, these figures basically show the difference between the number of parameters and how it's now basically able to do a few-shot learning that it wasn't really able to do before. I'm just actually interested that they have like well, they've drawn the, let's say, a line between their actual data points. Why is there a line between 0 and 1 examples in the context? Which is just funny. Doesn't matter.
Yeah, I know what you mean. It was everywhere.
But yeah, as you can see, if we go from 13 billion parameters to 175 billion, it scales quite well. for now you can actually do one-shot learning, and even zero-shot learning is a lot better than 1.3 billion parameters at whole. So something there has been like a what's the word, a chain, basically paradigm shift, I guess, kind of with this new scale. That you can do things that you couldn't been able to do before. So I find the figure 1.3 a bit funny. So this figure is basically shows aggregate performance of all the different benchmarks, and it seems it scales in the end, but it just seems also very random.
Yeah. That's they also kind of described that this is not like a representative, or this is not. I don't know how to say it, but they kind of said this is not very scientific. Don't try to read too much into this, because the problem was some problems did scale, some problems they still did not. I would put it like that. Some they showed, let's say, close to state-of-the-art performance, even with no fine tuning, while at some others did not. They did not succeed too much.
And this is actually, look at these two figures. This is actually a nice thing they did, because if you look if you would only have the above figure, you would say, oh, this is nice, like scalable. But this is just like a simple example that most likely is the best example they have that shows the best scaling, and then you can see that actually the difference isn't that huge. They're basically doing zero-shot this.
No, that's parameter. Okay. Yeah,
this is parameters, and you can see that there isn't that big of a difference actually. And there is still, I mean, goes from zero-shot goes from 20 to 40%, so it's a 2 times difference. But you know, from 1.3 from 1.3 billion, it's a smaller difference compared to this difference here.
Yeah, of course. But you can also, if you look at those parameters, then the last step, 13 billion, which was roughly, GPT-2 was 1.5.
You said 10x, so it should be like 30.
No, but it was 10x on the state of the art, but I think GPT-2 was actually 1.5.
It doesn't say GPT-2 here.
1.5 billion. Quick Google help. So it's on this line. The GPT-2 is probably near this 1.3 there. But in the intro, they talked about other methods. So the other people had been scaling after GPT-2, and I think they got up to 11 billion or something like that. And then this went to 175 or something like that. Yeah, so 175. So basically, compared to, let's say, GPT-2 there on the plot, which is, let's say, roughly this 1.3, then the performance increase is almost double. So
100 times the parameters for double the performance.
2 times the accuracy. But of course, accuracy doesn't scale also linearly. So if you go from 98% to 99%, you're reduce your errors a lot more than 1%, right? So also important to keep in mind, the higher you go with the percentages, the more they quote unquote matter.
Also, it doesn't go twice, it's like 1.5. But still, I think this graph shows you that you want to fine tune it, at least for now.
Yeah, or
so I mean, in the end, 40% accuracy is bad, or even 60%.
Yes. But this is all along all problems. You can see some problems scale with this last step very well. It's very grayed out, and I think most of the impact comes from these well-scaling problems, most likely.
Yes.
So interesting, at least.
Yes, and here is still basically talking about the same thing we talked about, the difference between the shot learning types and like a regular fine tuning. So in the zero shot, they don't train on the examples anymore. But with fine tuning, you would basically have I guess you would have another training set with you would train on the exercise already, basically. Or do they?
They give
example tasks. Okay. So
yeah. In the fine tuning, you would do the first part. Let's say in this case, you would do the first part, but then you would have. And you would consider that pre-training, and then you would give it an example of. Then you would still train the network on a specific problem, basically, and you would actually still update the model weights. But few shots, 0 shot, 1 shot, you don't do any training. You just give it context.
Yeah.
Which is fun, conceptually totally different.
Yeah, and for a model of this size, then this would be a bit more expensive to keep training it for every example.
Yes. One part is expensive, but the other big problem is fine tuning assumes that you have labeled data to fine tune with. Although they might be able to do, let's say, extended few shots somehow, somehow in an unsupervised manner, but the classical fine tuning is with supervised data. So
otherwise, it doesn't.
Yeah, and the important note to make here also is when they talk about traditional fine tuning and fine tuning in general, and they did mention that most of the state of the art today is done with fine tuning. And they try to do without fine tuning. Then in the fine tuning case, they still use a very similar neural network architecture, because this is just performs so much better than everything else. So everything is transformers end of the day in natural language processing world. Basically.
It will be interesting to see how well this model does with fine tuning though.
Yes, for a problem, but then they wouldn't be like, hey guys, take this GPT-3 API and do whatever the fuck you want with it, or help it write code for you, or like stuff like that, which is this codex thing, which is cool. I'm in the beta, but I have not.
Well, I think I'm quite sure that it's fine tuned already.
Yes, that probably.
Yes.
I agree.
I mean, if there's a company that will use GPT-3, I think most likely it will fine tune it. Maybe for the prototype, not to see how it works, but to actually use it, of course they will fine tune it.
Yeah, but let's say if I wanted to make a program, I would not fine tune it.
Of course, because you don't have the money to fine tune it.
Fair. Yes, yet.
Want to say something?
No, I'm good.
Okay, and here this was I guess the only funny part for me in this article, as they have basically they're showing the different models that they train to see that basically to have the same architecture and to see how scaling affects the different architectures, how the scaling affects the results. And the funny thing is that so they have GPT-3. Basically, that's the main GPT-3 is the one with 175 billion, and they call it GPT-3, which is the biggest one. And all the other ones are like, and starting from the GPT medium and GPT large and GPT extra large. So for me, logically, or maybe I would say, talking about language, then maybe GPT medium should be like GPT-3. And if you have like GPT-3 large, then it should be bigger than GPT-3. And then they have GPT extra large, and then they still have like extra numbers or whatever. So this is just
mega.
Yeah. It should also just be parameters. I think that would make more sense.
Yeah, that's probably some historical reasons combined with now it's funny already for them also.
Yes.
By the way, actually, from the article point of view, one thing I really liked was the reference style. Interestingly, because they had year numbers in the references. It was very nice to have.
What numbers?
Like right in the text, like they had reference, then 3 letters, and then a number. So it was short, and at the same time, the year in this context was quite important to know when was this paper when was this info published. So
yes,
that was nice.
I think most likely the citation style is depending on where they submitted this. If did they submit it anywhere? Or is it just because it's OpenAI, they don't have to submit, they just have to put it on archive?
It's a great question, yes. Which one they did? I think they might have whichever one. I actually have a point about that under the 4th paragraph section, so when we get to that, I will bring it up.
Okay. And yeah, all the models were trained on the same amount of data. They didn't really have a figure for the data itself, but they used Common Crawl and Wikipedia, and then they also some more high quality data sets, like they call it. And they also tried to let's say filter and work on the data set, so none of the test examples are in training data, though that didn't work out that well for them, but that will be talked about later. But yeah, basically then they ended up with 45 terabytes of mostly English data, with some, I guess, translation inside there as well, but still mostly working on English data.
Yeah, but it was interesting that so an important thing they did was this data curation, which seems to be critical as always. Try to do as much filtering as possible so they would not have any duplicate. So let's say you have two data sets. If you have duplicate information, you might accidentally put it in both validation set and training group test set. So you might corrupt your results. So they try to avoid it as much as possible. As you mentioned, they didn't succeed fully. According to themselves, they also had a bug which created so even if they had discovered some, they didn't filter it out properly, but they also evaluated the impact of what that might be. But we'll talk about that under the 4th section once again. But yeah, they also added Wikipedia, which I guess was relevant.
I mean, yeah, I think Wikipedia has been there always, so always used. And then they also talked about how much compute they used during training. So then they end up with, I don't know how much is it then, 3,000 petaflops per second for a day, which Henrik says isn't a lot. It equals 1 human or 150 trees.
No, it's 1 human, 12.5 years of CO2 equivalent. And but I think it's we discussed it before a bit because it's a funny thing to think about, where the reporting around this was very, very critical about the amount of energy used and the amount of pollution caused by this. But this is more to have more equivalence. This is 2 or 3 cars, I think. Let's say an average car driving 200,000 miles, maybe.
Kilometers, maybe. I don't know what's the average mileage.
Yeah. Yeah, so still something like that. Let's say 2 to 4 cars, and the ballpark will be right. Which, I mean, I'm okay with having less cars. So I think if you bring equivalence in, then it is not that bad. So in the large scale of things on what this can be do, and my claim here further is there are a lot of compute advances that have been made since then. You could scale it up with that, maybe even 10 times already. And then with energy costs, you could probably scale another 10 to 100 without still it having negligible impact. Or sorry, having a negligible impact on anything else.
So yeah, compute gets more increasingly efficient all the time because a lot of money is being pumped into the development of more specific GPUs.
But my point is, if in 10 years somebody scaled this 1,000 times without it still having major negative externalities, like I say major, of course it has negative externalities.
What doesn't?
Yeah, exactly. But I think it is possible to do. I estimated it to be a lot worse, is my point. I estimated them to be on some kind of a threshold of only OpenAI can do this type of thing and no one else can, because they got some fucking huge funding for to do this compute specifically. But actually, I would estimate there to be many players who could make a similar model if they not a research group, but because research groups funding usually you don't want to spend it all on on compute, you would rather spend it on people's salaries.
But it's still, in the end, it's still lots. So we calculated this to be about purely on the GPU standpoint to be about $320,000
for energy. Yes.
Yeah, for specifically, and then you have to take account that there, of course, this isn't the full energy demands. You have other energy demands in there as well. But in a server farm, if it's let's say made logically, then you can actually use the excess heat to warm up a building next to a server farm. If it's someone actually thought about it a bit before they built the building.
And so on and so forth. You can make the server farm in a place where you get a lot of near Norway's hydropower and so on and so forth.
Or sun in California, in somewhere warm. Yeah. But yeah, they used Microsoft Azure server farm, I think. So Microsoft is one of the big donators into OpenAI, or big contributors. But yeah, even they said that it's still, I mean, it's still expensive in the grand scheme of things. Let's say compared to some funding, but they said that they found this contamination with the training data, and they couldn't like retrain their stuff because it was too expensive.
Yeah, and also then they would have, and it's research expensive because it's time expensive.
Yes.
You still need let's say you have a server of like some amount of GPUs, you still maybe want to train it for 100 days or something like that. It depends on the amount of GPUs in the server, but so the biggest problem of I think is time actually.
Yeah, I think if people weren't doing, I think it's like the actual cost of training GPT-3 is in the millions. I don't know if it's 10 million or more, most likely less, because you have to take into account amortization of the infrastructure, the people working in the server farm, the scientists and engineers have to also how to optimize the whole data, optimize the training, the data flow inside the server and everything that takes money. But yeah. But this is an interesting topic. It would be nice to have the actual like, because they had in later they have a very pointless chapter on energy cost that doesn't say anything. So it'd be nice to actually know how much does it cost to train OpenAI if you take into account everything.
Yep.
Or GPT-3, I mean.
Yeah, but it might have been hard for them to separate, let's say, the final training and initial tests and validations and so on and so forth, because you could claim that this is like almost like a research model, not like a production model. But it's definitely an interesting topic, and in the future probably will also be a big thing, like how much compute and machine learning actually take, and it will take a lot. And my main point still was that there is still room to scale, even with the current hardware that we have and current everything current.
Yeah, there's room to scale, and most likely it will cost less. I mean, this costs less now, right?
Yeah, a lot less if they were able to leverage the compute. And the second part is inference will be cheap. So this is only training.
Cheap-ish.
Cheapish. With inference, they also talk about this, that it is still a bit annoying. But at the same time, you can, let's say, you have some free APIs for GPT-3, like with I think some limited amount of users or something like that. But still, that means that the inference can't be too expensive if they provide it for free.
Yeah, it will be interesting to how. So currently we're still basically let's say hot fixing GPUs to do neural networks. Well, kind of. But it will be interesting to see once more and more dedicated architecture show up. Like, for example, I'm most interested in the company called TensorStorrent. The only reason I'm interested in the company is because who is one of the main guys behind it, or was hired in there. Mr. Jim.
The question. Okay.
Mr. Jim Keller himself. So I would say one of the most important people in the hardware in the current day and age. So it'll be interesting to see what comes out of that.
And talking about transformers specifically, the latest announced NVIDIA things, H100s have transformer units. So
H100?
Yeah, the thing that they announced last week, the week. I think that is. I'm not sure if they are already shipping or when they will be shipping. But,
I will put it up here. So the first graphic they have is at least very.
I don't see it yet.
You don't see it?
No.
Can you see it now?
I only see thingy.
Weird.
Now I see it. Yes.
Okay. So yeah, they're saying that compared to A100, it's a lot better.
Yeah, they have like specific transformer engines that are supposed to work better with this architecture in whatever. Well, I don't know the exact details, let's be honest.
Yeah, so this is some kind of transformer network that they're talking about.
Yeah, they have transformer engines everywhere, and when Jensen was talking, he also kind of mentioned transformers about 100 times. So would scale with this thing definitely.
Also, it would be interesting to see how this. I mean, it scales currently very well, but it's very specific to transformers. Then it would be interesting to see how well it lasts if we go on to the next thing. Yeah,
the interesting thing is how well do transformers scale to other problems than natural language processing. That will be. I know that people are looking into it, but I think still there are definitely already other applications than natural language for transformers. So if they are putting this much faith behind it, that means their internal research also probably shows that transformer is awesome, and a lot of customers want it.
Yeah, I mean they themselves make. Well, their main thing is, I guess. Well, yeah, they have a lot of products, deep learning, neural network products themselves as well, besides the hardware.
Yep.
I guess the most known one for the general audience is the deep learning supersampling, or whatever they call it now, which is basically upraising your video games.
Yeah, but they do a lot of robotics, and
yes,
many self-driving car companies are actually NVIDIA self-driving things, which they don't call themselves that, but they just basically use models that they have.
But this is the different interesting part. Like I said, we're like hot fixing GPUs to work to neural network stuff currently. And also like the general versus fine tuning is that Tesla also used to use, I think, NVIDIA stuff. And then they were like, nah, Jim Keller, please help us. And Jim Keller was, okay, I'll make you something a lot more efficient.
Yes, but will their approach scale? Will they keep making GPUs? Well, I think we will see in 10 years if it was a good strategic decision or not.
Yeah, I mean,
Because-
if they, I mean, if they have a, if they have a very, it's basically like building an ASIC or an
Yeah.
application-specific integrated circuit.
Yeah,
Yeah.
short term they definitely win, but will they be able to maintain it and innovate long term? Will be interesting.
Yeah, I mean, yeah, it's always, I mean, okay, Tesla is a bigger company than it is actually, but it costs a lot to develop your own hardware.
Yep.
But money Tesla does have currently, so not a problem there. Tesla could buy NVIDIA. Basically.
I'm not sure about that. NVIDIA costs also too much.
I mean, yeah, both are overpriced.
Yeah.
But yeah, here is also another. Basically, we can see that. So they talked about how we're still like scaling well, and so I don't know when they at some point when they were doing the GPTs, they discovered that it scales, the performance scales with compute and size and everything. And currently the scaling is continuing. So you can see how basically compute, I don't know, how it scales with compute.
Yeah. But under figure 2.2, there is an important point that I raised before, that they are using much fewer data for the same amount of parameters in the model. So their 3 billion parameter set is similar, is trained with similar amount of compute than one that had 10 times less parameters. So they also kind of were able to get 10 times gain in a few years just from, let's say, training process optimization, which is also interesting.
Yes. Okay, and then we actually start, I think, going into the first examples on what they showed. Basically, the results of their training. So
yeah. So first up was language modeling category, I think.
Yes.
The categories then also bit same way that they did.
And the first one was on Lambda. So the Lambda dataset is to model long-range dependencies in text. So basically asking the model to predict the last word in a sentence, which requires reading a paragraph of context before. So if you look at our episode number 2, I think, where we talked about curriculum learning, there they also did like text prediction, but there they had like 4 words and then you have to predict the 5th word. And this is a bit different. You have a whole paragraph of text and then you have to predict the 1 word based on that paragraph.
Yeah. I think the important point here that we forgot to mention before is this is like a very good follow-up to our memory stuff, because transformers, you wouldn't call it memory, but this
But you would call it memory.
This attention is all you need. Is kind of a dig at memory. It's like, no, you don't need memory. You need attention, basically. So this is kind of, you have the context, but you don't need the full memory or some permanent storage somewhere, but you need this kind of context and recent information.
Why not both? I was wondering what would it look like if you had like GPT 6.7 billion or 13 billion with memory and attention.
Yeah, fair point, but not there yet. But this is kind of it's like a different way to solve the same problem, is my point. And here it's like even the use cases are similar-ish, like as you described. Like you need to remember a set of like a paragraph of information, because like the relevant information might be like 20 words back that you actually need to connect to, so on and so forth.
And here in the figure we also see SOTA means state of the art. So if you have a fine-tuned architecture for, can it be fine-tuned if it's zero shot? I mean,
well, zero shot and fine-tuned, yes, it can be, because then you so a fine-tuned network, after it has been fine-tuned, it usually does zero shot, like depending on how you feed the information to it.
It's not really zero shot.
Because usually, like, the reason why this this zero shot distinction is made in this paper is people don't usually give context in before they actually ask for the result, but they have trained it for this specific context. So you usually don't need to provide the context because you train it for a specific context.
But this, I mean, it's kind of weird still to call it zero shot if you trained it for it. If I understand correctly.
Well, yes.
You understand it correctly?
I think that the way I got it, I agree with you that it's weird that it is called zero shot state of the art because it is just state of the art.
Yes.
And okay, they probably the state of the art zero shot state of the art probably means that it is uses something a bit different than what they had above their like definitions of where and how they use zero shot and when they don't. So it should be clear when you think it through, but
let's see if we're correct or not, if we're just saying something wrong. So this is taken from my Project Turing, which is well, wait, I will search for the correct one until you can keep talking about it.
Yeah, sure.
Is it 17 billion? Okay, it should be this one.
Yeah. But yeah, the important part here is that they show like incredible performance with this type of problem, because here from 70% to 85-ish% or even more, that's like a huge increase. That's 2 times less error rate.
Between what it is between
few shot accuracy versus previous zero shots state of the art. So yeah, 18% increase. But if you think about, that's almost like that's so much less errors. Almost 3 times less errors.
But well, depending on. I mean, yeah, it should be better than zero shot. Let's see, wait. But I think maybe it's still basic. I think this is. It's still like, I guess it's still a general language model. That is the zero shot. So basically, I think.
Okay. So they also have like a universal model that has the. So they don't do. Few shot and that type of stuff, or
so here it is. Can you see it?
Yeah.
So the Turing natural language generator is a 17 billion parameter language model by Microsoft that outperforms the state of the art on many downstream natural language processing tasks. We present a team of demo of the model, including freeform generation, blah blah blah.
Okay, so very similar to this, but
we see OpenAI GPT-2 here. And then generate 2020. I think it's the same idea. It's basically like we were talking about before, going bigger.
Yeah.
And we see zero shot. Many web search users are accustomed to seeing a direct answer card displayed. Okay. I think I misrepresented the figure in the beginning. So this is basically another. It was the best state-of-the-art language model, general language model, that was trying to do zero shot on this problem. It would be
but people hadn't shown basically few shot results, so that's what they show. By the way, if you do few shot, this does even super well. So that was like it was a combination of the zero shot does better, one shot does worse, which is also important here. They also tried explaining that. With one shot, you aren't actually able to infer the context that well. So it does worse than the zero shot. But with 15 examples, then it starts performing really well.
It's interesting, yeah. That actually the architecture in general, like it seems better than the Microsoft one, as it does. That was 17 billion parameters, and it's up by, let's say, 5%.
Yeah,
I bet 5%, a few percent better than.
It might have been also their data pruning. And with Lambada, they also commented that they might have had some data corruption. But
okay, this was one of those.
Yeah, but they did an analysis and it showed only maximum error from that would have been 0.5%.
Okay, so this is basically the same then, compared to some others. But so basically, in the architecture itself, or at least the way they trained it and the architecture.
Or the training data. Importantly, training data can also have a huge role here. But yes, I agree.
Because even the 3 times smaller version, I mean, the 2.6 billion one is basically as good already with the 17 billion parameter one. And with the few shot one, they also always said that the K, or how many examples they gave in the context, was they just tried to find the best one. So in this case, showing giving a 15 example context was the best performing few shot. What's the word? Example, I guess.
Yeah, and some basically say in most cases bigger is better, but not in all cases.
Yes.
And and also they probably have an interest of not putting the maximum amount of examples in, because that's not, if they want let's say they want to generalize the algorithm as much as possible, then more examples is not that great. You want to have, let's say somebody needs to define a problem to you. You don't want to give as many examples as the network can take, but you want to provide as few as is possible to get the best result.
I mean, that's why you saw zero and one shot. But I think in the few shot, I did not take this into account, because in many times they said they filled out the context. Or basically. Yeah. So I don't know. I guess this comes down to my ignorance on transformer, but I presume this is something to do with how much can you fit inside something yes, transformer.
Yes. How much fits in the context window. So few shot is you fill the whole context window.
Yes.
Like the maximum amount of maximum K is full context window.
Yeah. But anyways, we can already see that it would be interesting to see also. I guess one thing that a bit bugs me, it would be nice if they had like, okay, maybe they didn't have like few shot state of the art, but maybe a fine-tuned state of the art would be also nice to have here. But I guess that is maybe human level, so there's no pointer or something. Did they say anything in the text about it?
No, because it doesn't have a supervised training set available, so that's why you don't have it.
Okay.
So you can't do it. That's the problem. Can't fine-tune it because you don't have the data.
Okay. Then next one was trivia QA, which was, there were so many things they did that I don't remember all of the specifics.
Yeah, so they had many question and answering ones in a row.
Yes, yeah. This was under closed book question answering. If you can you describe what is closed book question answering?
That means you don't have access to knowledge bases. So instead of Google search, you don't you aren't able to check Wikipedia.
I mean, it checked Wikipedia once and it had to remember what it remembered.
Yes, yeah, but the network is not big enough to to memorize Wikipedia, so it has to memorize what it knows. And then closed book basically means that you don't have access to any knowledge base, but you just try to answer questions. Here it did not perform with question answers. It mostly did not perform as well as other things. As fine-tuned models, it kind of the few shot one came close though.
I mean, the few look at this figure. At least trivia QA, the few shot did better than fine-tuned. One shot did as well as fine-tuned, and zero shot was far behind.
Yeah, the trivia QA one it did very well in, but the other, but the trivia QA one also has I think they describe it has a hidden let's say amount questions. So it they were afraid that, or the hidden like set of data. So they might have accidentally gotten information in their training set that matches that.
Because so there is a figure in the paper on figure 4.2 where it talks about how clean or dirty the data set is, meaning and how much basically examples were there in the training data, and it doesn't seem to show trivia QA here at all. Okay, I mean most likely it's one of the data samples here, but doesn't show it specifically. So
yeah, because it was a special case because they don't have the data set.
I mean, yeah.
So it's like an external data set where you got kind of. I think that was that one. I'll confirm that this was about trivia QA that I'm talking about, and not some other.
Okay, yeah. Final results are reported on the test set when publicly available for each model size and learning setting. When the test set is private, our model is often too large to fit on the test server, so we report results on the development set. We do submit to the test server on a small number of data sets, Superglue, Trivia QA, and PI QA.
Yeah, okay, maybe I was talking about another model. Anyways, the important point here with this is that they did no fine-tuning on the question and answer data set.
I mean, they never do any fine-tuning.
So. Yeah, but other ones have. So other state of the art has done basically fine-tuned training on the, let's say, the data set.
Yeah.
Even if it's closed book. So it's like, answer me questions about this very specific field and train for that very specific, solving questions for this very specific data set. That's like, I would say that that makes this GPT result even more impressive once again.
Yeah, I mean, yeah, it basically achieved state-of-the-art results. And this is basically, we're not going to go through all the examples because I mean that would be a bit pointless. But here we can see a trend. It's basically a general model with a few examples for conditioning. It can achieve state-of-the-art performance on some examples, but not all. Let's try to find an example where it doesn't reach state-of-the-art. Most likely in translation, but it doesn't show the. Yeah, it was actually translation is interesting because which also makes a lot of sense. It always does better in translating into English. So we're looking at a graph where basically if we're talking about GPT-3 with 175 billion ones, then if they're translating into English, it has a very high score. I don't actually know it, so it's as 40 BLEU, which I do not. What was it? What did that mean, Henrik?
Yeah, you asked. I didn't Google.
There's some kind of weird score that they use in.
Yeah, number between 0 and 1 that measures the similarity of the machine translated text to a set of high quality reference translations.
But this is, then look at multiple, because this is not between 0 and 1.
So I think this is scale divide by 100.
Do you think it's that? Do you think it's like a 40%, let's say, in a sense, accuracy, and how perfect?
Yeah, but with translation, it's weird.
Yeah, I know it's weird.
It's a score. You give a score to a translation, and it's like a translation score out of 100, I think, maybe. But this is still the one kind of the to English is state of the art numbers, or very close to it.
Let's see. Wait, how to? Can you see? How to?
Yeah.
How to interpret multiple EU score? The geometric mean of these precisions multiplied by the brevity penalty calculated according to the length ratio. Okay, never mind. Anyway, it seems up to 100.
Yes. So because you care are the words are in correct order and so on and so forth.
So as you can see, we're not we don't know much about translation or natural language processing. But the interesting part to take out here, which makes a lot of sense, because this is trained basically on an English data set. So of course, whatever it writes in English, it writes better than if it would have to write the same thing in whatever Romanian or German or French.
Yeah. But at the same time, it has been able to, in some context, connect that in a way that you can translate to English.
And also, here we can see also. So I would say that it has seen more French data than German data, and more German data than Romanian data. But apparently, I did not know this before, that there is a lot of Romanian research, I guess, in this field. That's why they also have Romanian here.
Cool. But yeah, awesome result. Play yes. Like that and move on.
I don't know. I don't know if it's an awesome result because they don't really show any other.
There was a table that said
okay.
state of the art numbers, and they to English they outperformed state of the art.
But that was the issue, that they didn't really know where to look at. They stated themselves that might be, we think it's state of the art because that's all we can find, but we can't guarantee that.
Yeah, but at the end of the day, it's basically you should take the API and compare it to Google, which is basically pretty good. And it's not a state of the art, but it's like that gives you an intuition of it probably performs better than
that. But yeah, actually, and then yeah, so they received like state of the art in most of the stuff. I mean, not state of the art, like near state of the art. And now I'll try to find an example where they actually did shittily. So, for example, in ANLI round 3, so ANLI, what did this mean?
You mean natural language inference, right?
Yes, I think so.
There it was ability to understand the relationship between two sentences. So overall, they described.
Can you give us an example?
I'll try.
I can't find it myself correctly.
There isn't that great of an example here, but I will try to.
Okay, for example, whether a word is used the same way in two sentences. Other than VIC, whether one sentence is a prephrase, another. Whether one sentence is a paraphrase. So basically, so I don't know if this is that specifically, but whether one sentence is a paraphrase of another, or whether one sentence implies another. And so this is natural language interference, and the round 3.
they described it a lot better, like the limitation. They described this limitation very well under in the conclusion part, where they basically said that it doesn't. The GPT-3 model doesn't do well in quote unquote comparison tasks. So if it has to compare two things, or if determining if two words are used the same way in a sentence. So this is what you pointed out. Or if one sentence implies another, I think that is the only. This is
so one. No, yeah, and so I guess so that is all natural language interference in general, but unleash specifically means adversarial natural language inference, not interference. So basically, this is made specifically difficult for machine learning, if I presume correctly.
Yeah. But they also have that they that this is like a specific problem that where a different type of architecture outperforms. They called it bidirectional architectures seem to perform a lot better in these type of problems. And they also basically described, we might want to do that. This might be a great direction for GPT to take. So that here I wrote one note here where it's like potential GPT-4 bet bidirectional model.
Can you quickly say what does that mean, bidirectional?
I did not Google it, so I would be talking out of my ass. So,
I mean, I talked about it a bit, but
yeah, but I didn't understand it fully.
Yes, but I guess how gradient descent is done.
Quickly, it seems that you put in the sequence in a forward direction and like also in a backward direction, and that's all it does. And it's like so like let's say you have a sentence in one way, you also put the sentence in the backwards basically. But this is how it's used in.
And there's, I think, if I remember correctly, there are you can even go bigger than bidirection. You can even go up from there.
Yeah, because it's very interesting that it does anything. I'm very surprised.
No, I actually remember learning about it in my neural networks course.
Okay.
I think I remember it was interesting then when I learned it as well. But yeah, I don't exactly remember as well the details.
Yeah. Anyways,
it's basically
I didn't analyze it. Yeah, I didn't analyze it too much, but overall, that's where they point the finger at when GPT-3 has some limitation, and I think that's an interesting, like bigger limitation, that this comparison or between different sentences, different contexts, basically.
Yeah. So yeah, for example, one of the nice examples they had. GPT-3 can't answer a question like, will cheese melt in a refrigerator? Because it kind of just doesn't understand. That has some like, so yeah, that they were talking about also like expanding from text to other sources of media sources as well, which is interesting. But then basically it does kind of basically random with all of, I mean, the accuracy is as good as random guessing until we get to 175 billion parameters and few shot. Then it does a bit better than random, but not much. And actual fine-tuned state of the art is still a bit off.
But as you can see, the fine-tuned state of the art is also pathetic.
Yes. Yes.
Compare if the random guessing is 33%, then getting to 48 is like, yeah, guys, we did it.
Every second one you get correct, not every third one. Still better.
Yeah, but cool. That it is so. It's cool that there are problems that are so bad with this architecture is so bad that the problem is set up in a way that random guessing is 33% correct. Yeah. You can put it like that. The problem is set up in a way to be very easy, because random guessing is 33%. Otherwise, you would probably get some like results. But it's like, oh, we got 5%. No, we got 6. Ha ha ha. Fuck you.
But yeah, we still have to remember this is the adversarially mined natural language inference, so specifically made hard. I wonder how to make it generally hard for machine learning algorithms. It's interesting. I get how you those adversarial things for a specific neural network, but how do you like generalize that? I guess you see what they do it worse than, and then you only keep those examples.
Well, you can ask very general knowledge stuff or something that requires you to have some specific, let's say, like will cheese melt in a fridge is a great question to ask a neural network. It requires some underlying knowledge about kind of what, like that's a very hard question. It requires so much contextual understanding.
Yeah, but this was still done somehow automatically.
Yeah, fair. Is it?
I mean, it says adversarially mined natural language. I mean, we would have to look it up.
Yeah. I mean, I didn't go all through so many of these things, but yeah.
Let's see. Wait, in a second, I will see. So from the so it's from Facebook. We introduce a new large-scale neural network inference. Why do I always want to say interference? Inference. Benchmark data set collected via an iterative adversarial human and model in the loop process. So both human and model. We show the training models on this new data set, these two state-of-the-art performance on a variety of popular NLI benchmarks are posing a more difficult challenge with its new data set. Our analysis sheds light on the shortcomings of current state-of-the-art models and shows that non-expert annotators are successful at finding their weaknesses. The data collection method can be applied in a never-ending learning scenario, becoming a moving target for NLU rather than a static benchmark that would quickly saturate. That's a good idea, though.
So natural language predicts something, and the humans try to confuse it as much as possible, and then successful confusions are
So basically, adversarial NLI data collection via human and model in the loop and enable training. Hamlet. How did they get Hamlet out of that? The first step to make up one round of data collection. In step 3, model correct examples are included in the training set. Development test sets are constructed solely from model wrong verified correct examples. So target label context.
If the model gets it correct, it goes to train. If the model gets it wrong, it goes to train.
Person. And if the verifier agrees, then it goes to training.
Yeah.
If he disagrees, then they throw it out. But how do you get the test set, development set?
So you separate that into. Wait. Model figure. First, the writer writes examples. So there is a writer trying to write complicated examples. Then it gets model feedback.
Whether the model understands it or not.
Yeah, so the model feedback is so it's
okay, so a person gets a target label and context. It then writes some bullshit about that.
Mm-hmm.
The model gets the same things, and then we can see if the model predicts it correctly or not. If it's wrong, so if it's correct, it goes into the training set. If it's wrong, it also goes into training set. Isn't the point to only for the wrong ones to go in there? Why would the correct ones go in there? Isn't this a place to be?
I'm also confused now.
But it goes from the right side. Is there a difference? So I would guess that you want to use the ones that the model doesn't predict correctly.
Yes, I agree. I'm confused.
For the first round, so the rounds are basically how strong the model is, where they created this one context. Okay. Anyway, interesting.
Yeah. It seems like it wanted to say everything, most things that the models get wrong, they want to add to dataset, but they didn't understand it from the figure. Also, they had writer, but then later they had different rounds with different models. So,
yeah, and context and stuff. So basically,
should actually read the paper through.
Yes, understand.
It. Yeah.
But basically, it has 3 rounds, and each round was basically a more difficult data set. And this is looking at the most difficult data set in the ANLI. And also tries to do arithmetic, which was interesting. Not that well. So these are the things it doesn't do that well. So basically, it does well if we're talking about like few digit stuff. If you get to higher digit stuff, it does quite badly. So if they said that when they looked into the model, it seems that it does mistakes with carrying. So it does actually try to do figure out a procedure for let's say addition, but it makes mistakes like carrying a 1 or something like that. So that's why the accuracy basically shit.
Yeah, neural networks models have always been shit at that. I'm just surprised how good stuff like Wolfram Alpha is. I'll turn it around. I'm just surprised how good they are.
I mean, Wolfram Alpha just most likely doesn't use a neural network to do addition, right?
Yes, I mean fair, but their contextual understanding is also great.
Yes.
Math wise, you can ask, you can solve many problems which are.
Yeah, but that's the thing. So they understand the issue and then they use dedicated stuff to solve the issue. Yeah. So different.
Yeah, I mean.
Basically, this is like end to end. That is end to a specific.
Yeah, but it's funny. You tell the neural network to learn math and it sucks at it.
Yes.
Yeah, it always does. Without learn if you tell the neural network to learn math, it sucks at it. Although intuitively it should be very good at it.
Yeah. Interesting. Anyway.
I will get stuck at this why neural nets bad math again question, which I think we once discussed.
Yeah, I think it's with the current architecture. I don't know. I think in the differentiable neurocomputers they didn't do math, right? So I would be interested to see how they do that, or maybe if you want to do. So that was I don't know if it's a good idea or not, but just playing around with the activation functions. So if you have different activation functions, can you get more interesting results? But anyways, it doesn't do well. Math is bad for neural networks, ironically.
Yeah.
And it doesn't also that good with word scramble. Some parts of word scramble were quite bad. Mm-hmm. So as you can see, depending on whatever the exercise is, it does well or bad.
Yeah. Did you see the reversed words one where it scored almost a 0?
Yeah. It's interesting. That didn't change at all with the size. It seemed to be at 0. But so they did all the different things. But yeah, actually this one I guess was the most for people in some sense the most interesting one and the most let's say most dystopian one is that they let the network generate text depending on some kind of title and subtitle, and then people had to understand whether this was written by a human being or a neural network. And this is one of the best performing paragraphs they had. And I was reading it like, I will most likely understand which one it is or not. So this is about United Methodists agree to historic split. I'm going to read this, but yeah, it's an interesting text. And but I think they also said that the people got better at understanding which one it is, a neural network or not. So they learned to understand what to look for, I think.
Yeah, that's 100% like the case with any bots or computers you play against in games. Like you learn what the computer does, and you see humans are great pattern recognition machines. And if you, especially like we would then be training against, it does this thing all the time. Okay, this is a bot.
Yeah.
So using the same stuff against them.
Yeah. And so the thing we talked about before already, and so the interesting part is that they had an issue with what's the word? Dirtiness of their data set. Basically, if contamination, yeah. If they had like anything that could, let's say, prep any examples in the training data that could prep the model to understand the test they were giving it. And the biggest issue was with, I guess, with some of the, for example, with QUAC. So basically, they said like 100% of the data was contaminated, which was interesting. They also had some explanation for that. And here we can see that in most of the cases, it doesn't actually matter. Like after cleaning, so they basically cleaned up the data. Doesn't matter that much. Like a few percentage point difference, but it can do a bit more. You can see that, for example, for reversed words, where most of the data was actually clean, it still did like 25% better on dirty data.
Yeah, overall, it's important that with reversed words, you can have the reversed words in the data set. It's still really hard to learn the context without, like, you don't tell it to solve the problems of reversed words. It can be in the data, but they're like, what the fuck is this bullshit? And at the same time, they had very conservative estimates in the how they calculated this percentage of clean data. So you shouldn't be like, oh shit, they are misrepresenting their stuff a lot. They were trying to be quite skeptical of their own results. Let's put it like that.
And this is nice to see that they're actually paying attention to this. I mean,
yeah, that was my point. My initial point that I said I want to raise on the fourth point as like, I think this is very cool that they do it, and I would say the reason why this section is so well written and why it has so much content is because they're not doing it through academia. They don't have anything to prove. They don't need to fake it till they make it. They just were like, okay, this is the model, and this is trying to be objectively as good as possible to evaluate the network, basically.
But I think also they didn't really have a choice in doing this, because if they wouldn't have done it, then this would have been, I think, their main criticism.
Well, yes, but I would say that they also figured, like, they did a lot of work to actually validate this thing, yes. Because they say, okay, like they basically say, in the same way that they are describing what they're doing, they're also like throwing shade at everything that has been done before and being like, okay, shouldn't you be doing like this type of thing? You know, when you're training on this, all of this data, shouldn't you be like validating that you are not contaminating? because they didn't reference this contamination part a lot by being like, and this is the best practice in this thing, and this is the. Now they're like, yeah, this makes a lot of sense, and we did like it's like I think they could have written a paper on this contamination part and how to avoid this had they been successful. What I mean by successful is that I understand they did all of this. They thought about this before, and they tried to do their best job, but they had a bug where in the filtering step. So even though they identified the problems, the data still got into the training set. So they didn't remove them completely, but it still shows that the approach that they took was like, I would go so far to say superior to what people usually do.
I agree.
So I would say I was very impressed by that. I was like, thumbs up. Don't believe it would have been done in the conventional academia without any pressure.
I think that's a bit harsh, but I think it's generally it's a good example of a good paper. A well-done paper.
I am very harsh on this note, but yeah, it's just shitty incentive structure.
Yeah. And so a big portion of the paper was, besides getting these nice results, and then also talking about how all the different issues with it. So one thing we looked at is basically the data contamination, which they tried to fix also before training, but they didn't decide to do it successfully due to a few bugs in their code. So they, after fixing those bugs, they took they couldn't retrain it because of lots of money that it costs, but they at least could look at let's say the test set results with cleaned up data sets and how much it actually affected the results themselves. But then it's also, they looked at different other issues besides data set contamination. They look at basically biases. So of course, if you have a lot of text, the text is written by humans. Humans are, every human is biased. But that is interesting though. If every human is biased anyway, then we'll.
Well, I think it's so the data will be biased.
Yes.
So the data that they infer from will be biased, and in some cases it is very hard to like draw the line. What bias is fine and what is not fine.
Because I think like if you're scrolling the internet, you will have biases in every way. You'll have let's say you'll have far right biases, you will have far left biases, right? So I wonder how they will like even out in the end.
Yeah, yes, and also so there is a question with biases. There is a question of application. Yes. I think that's where it gets fishy. So if you have, let's say you have a neural network and the police start using it because somebody sold it to them, and they're like, oh god, this thing predicts really accurately who is the criminal or not. It reinforces the same. Policemen have the same biases that the neural network will be trained on, and if nobody removes it, then you still get, let's say, biased incarceration results, and it will never get solved because now you have an algorithm that is also reinforces those biases that they have in this first place. So basically, what we can do with neural networks is we can do better. So you can turn it around. Analysis of biases is trying to quote unquote improve the human condition, not do the same thing, not do it as well as humans do, but do it better.
And so, for example, if we look at so some of the examples they did is this one they said like he is, so they fed the neural network with a beginning like he is or she is, or he is considered or she is considered, and then saw what kind of outputs the neural network got. So these are interesting. It's interesting. Both got, so the women are bubbly, but the men are jolly.
Yeah. So the thing on the right basically, or is the thing in the column basically shows the words that were specific for that gender, and I think the thing in the parentheses is the occurrence rate or something like that.
Yeah, average. Yeah. Okay, so.
So basically, and they pointed out that this is like women are more objectified, while men are less. Then there was also with more with gender, there was the occupation stuff.
Yes.
The occupation stuff where men were assumed to be more occupied, and well, the classic problem that more occupied in some specific roles, which is, well, something that definitely, let's say, in the context of the database of information that they are learning from, that will obviously be the result. But interesting point here was that larger models had less biases, which was very surprising. And that's went for all biases.
I think that is that is the thing I was talking about. That why it has less bias. Maybe it's just because with at least you can I guess if you have a larger model you can represent the data better in a sense. And if your data is skewed, it's not skewed in one way. It's skewed in every different way, and then it starts kind of, I guess, averaging out in a sense. But yeah, the interesting part in for example, in occupation was that they had like these prompts that this competent some kind of occupation was, and then we'll see what. So for example, this competent nurse is, or this competent director is, and then you could still look at if you get a male related word or a female related word. And for both the most competent, for both competent and incompetent occupations, both are men.
Yeah, but also the competent one had a larger deviation. So it was still it still brought out the bias, but it brought out the bias that somebody is occupied, therefore it is a male person that brought that out even more. So it definitely had, let's say, biases. It was interesting that larger models had less biases. It's a very quote unquote hot topic on what to do about biases, and really not easy to actually formulate. Nobody can formulate a very coherent response on what you actually should do. You can't make there are approaches to this debiasing, but they don't necessarily make the result better. So once again, the cool example is this police neural networks. Once again, where so we should debias the network. We'll remove the race part from it. But apparently, from the address, your name, well, their name, address, and you can pretty well predict your race from those qualities. So if they actually had the neural network predict the race, it was super accurate. So
it's a difficult issue.
Yeah, so it's really hard to get rid of, and at the same time, for all problems, you don't want to get rid of, because you can't also make the network not able to predict it, because then you can't remove the biases. So it's because in some case you need to anti-bias. It becomes a whole big topic and an interesting moral or ethical discussion on what you should actually do, which I don't think has been figured out completely.
Yeah. There's some more examples for what they did in biases. They basically tried to find did like the sentiment score on how people would describe like a race, like this race, this say whatever Indian man. I was actually wondering, is this Indian like India the country or like Native American? Because why isn't India the country under Asian? Which is interesting.
I think people in America classify Asian and Indian differently.
It's Indian.
And they usually classify Asian basically as China and Japan and Korea, and less Southeastern Asian, which is also very weird. So they have whatever weird.
Yeah, but it's weird because even if you look at the graphs, they're quite like similar, so they shouldn't have. It's also like so apparently I've learned that race itself is more of a social structure, then a biological one. Doesn't matter anyway. But just weird how they define races. It's like white, black. I get that, those parts. Asian, I get. And then you have Latinx, which even okay, I won't get into that. But okay, you have basically Southern Americans, which are also, I mean, they're white mixed with.
Yeah.
And
More
basically
mixed with indigenous.
yes, depending on the country.
Yeah.
And then you have Indian, which is Asian, and then you have Middle Eastern is different, but that's Arabic.
No. I mean, Middle Eastern is also very close with white, actually, and
well, Middle East, that's at least Arabic or whatever. But yeah.
No, but yes, but I think yeah, that's the point. That's your point of biology versus culture. Yes, I do agree with. So it's much more relevant if you do instead of saying race here, if you say culture, then you probably get a better.
So you're saying there's a black culture and there's a white culture.
Closer, yeah. In the same way that there is an Estonian culture and there is a different culture.
I know that there's an Estonian culture. Yes, there is no white culture. There's an American culture which is propagated everywhere, but.
Yeah.
Okay, let's not get into this stuff. Otherwise, we'll.
Yeah. Anyways, we'll get banned, but cancelled. 3 or 4 episodes in cancelled. No, I still stand by my word of culture is a better predictor of the effects that they want to track than race, and they should be using that when possible.
Yeah, basically it doesn't matter in the end because you can still look at this. Let's say these are just words, and we can find the sentiments for these words. And it's interesting in some sense, but I mean, they kind of like if you get into this larger one, you have like 2 groupings. You have whites, blacks, and Middle Eastern people, which I guess everyone is neutral on, and then you have Asians and South Americans, which people like more. Maybe these are all the Chinese bots that are promoting.
For promoting South America. So South American podcast and South American.
And then the last one they looked at was religion. This is interesting, actually. Like the most favorite descriptive words for atheism is feasts, and for Judaism it's Gentiles and then racists.
Yeah, but if you look at if you look at what they generated, they generate the sentences and they took out most common words. So they took out these are not. Well, they are descriptive to that part, but they are like say they usually have some context to it.
Yeah, but I mean, for example, this is Jews are whites, Jews are blacks. It's basically the sentences. But yeah, they had to wait.
You can show the. I will copy in the Buddhist example because the Buddhist example kind of shows the. Where are you in the thingy?
So yeah, I'm reading this anyways. Here.
I'm quicker.
I'm not in there.
Yeah.
Actually, I will do it like this.
Yeah. So so it still tried to, let's say, associate with, let's say, it still is like a classifier on those people, but it generates, let's say, quite high-level text, so it kind of has context. So, for example, this Buddhists are now divided into 2 branches, and then I think, probably you have, let's say, Myanmar and Burma, and so it generates, let's say, natural text, and then it like a lot of how do I call it? A lot of it's not like they have Buddhism and then let's say just predict the word what type of person that is, but it generates a text and then it has context and so on.
Yeah.
And so
I mean, all of these descriptive words, like, I think make sense. But I mean, like, for example, Buddhist, to get Myanmar, which is, whatever is going on there currently due to the whole civil war, or if you call it civil war, and at the same time of enlightenment, non-violent. I mean, I get how all of these words come to be. Maybe not Christianity officially, that is a bit weird. Or continue comments, what the fuck? I mean, I don't know why they chose these words, but
yeah, I don't know either.
That's a bit weird. But yeah, so anyway, they looked into bias, and that was interesting. I mean, that you have to, if you're doing natural language, and you actually want to fucking English. If you want to use it in real life, you actually use it.
Deploy.
What's the word? Deploy. Yes, deploy. Thank you. If you want to actually deploy, then you have to really think about where you're deploying and what effects will it have, and how to get the effects that are actually wanted, not the effects you're actually getting. And then you if you're dealing with people, you have to take the biases into account. Then you know, basically you have to calibrate it.
Yeah. There was also an interesting part here about if you remember, when OpenAI first launched GPT-3, then they were like, guys, we can't release this model to the public because this might be used by bad actors. And they also described that those threat vectors and stuff like that.
Mm-hmm.
And maybe and there are like reasonable, if you give GPT-4 or 5 to scammers, it will be really bad.
I mean, in GPT-3 would be better than they currently are, I think, the scammers themselves. I mean, it's just fun watching the scammer videos on YouTube sometimes.
Yeah, I also follow on Twitch some live scamming.
Yeah, but they didn't release GPT-3, right? The GPT-2 they released, but GPT-3 they didn't release.
They didn't release it, but you can use it as an API. You can interact with it basically, but you can't download the model.
But then with GPT-2, they at least found that they talked to experts basically in the field, and they found out that we didn't really see any. There was a bit of a jump, I guess, in kind of using it when it was in the news, but I guess it still has a lot of overhead that you have to like basically. It's not that good that you can't just check what it does. So you have to be checking what it does, and you have to like how do you prime it to give out examples that you actually want, right? So it still has issues for that.
But it's not that far away yet, and I don't understand people going like, it's not a problem. It's not you open and free, and everything is perfectly fine. This is the Facebook trap. Where Facebook is like, we don't control anything, everything's free, everything's wholesome and bestest, and then governments like abuse Facebook to spread propaganda, and there's like, but we are free, America, and then Arabian Spring and people dying, and okay, never mind, we're not free anymore. Enough. We got enough people died. We can't like use our own morals everywhere. Doesn't work.
Yeah, so that, I mean, that was the paper basically. Do you have any other prompts?
No, but cool paper. I liked it. Bit scary, very very impressive.
Yeah.
I would want to try using transformers and similar approaches in other fields.
Yes, and it's a very long paper, a lot of appendixes. So if you're interested in reading, it was I mean nice to read. At some point also, of course, you get the same kind of effect that you get with like a survey paper that is like example after example. Like okay, I get it. It does well.
Yeah, I
looking at figures.
Yeah, I went half examples, read rest of the paper, went through some examples in the end. So yeah, at some point, like, I don't care about natural language processing enough to be like, oh, this problem, oh, it solved this problem, oh, great. If I was a natural language person, NLP, then I would care, but I did not care enough.
Okay, well, thank you for listening, if you are listening. Next time, I think we will take 10 transformers. Would be nice to do, because I think that is most likely we'll do attention is all you need, and then maybe look at something more. We'll look at something more state of the art as well to see
we
where.
Can look at we can look at like a different application next. First transformer paper, and then application paper that maybe goes into a topic we know more about.
Yeah, or maybe we'll do it both at the same time, but we'll figure that out. Also, next time we will be live. We wanted to go live this time, but apparently YouTube wants you to wait 24 hours before you click on the word live before you can go live for the first time. So if you want to join us, then you can join us on the 10th of April at 2 p.m. Eastern European time, summertime.
And then all the edits we make on these videos won't come.
Oh, yeah, all the messy edits. So much editing. We won't cut off the beginning and the end of the video.
Fair.
Okay, so thank you for being with us. Check out the paper, Models are Few Shot Learners by OpenAI, and see you next time.